A special subspace that's related to the system AX equals 0 is something called the null space. Null means nothing, means 0, and it's kind of meant to imply that the right-hand side of this system is 0. So the definition of the null space is the set of all answers to AX equals 0. If I talk about AX equals 0, I'm going to think about it as a bunch of columns in the matrix that are weighted by some numbers. I've got a matrix with n columns weighted by a vector with n entries. Solutions x all have to live in Rn if my matrix is m by n. What I care about is the number of columns, because any answer then has to weight those columns. As the name suggests, the null space is a subspace of Rn for a matrix that's m by n. Why? The vector 0 is a solution to AX equals 0, and that means 0 is in the null space of A. Trivial solution is always a solution to the homogeneous system. If U solves AX equals 0, then when I take some multiple of it, is that in the null space? It is. And that's because of linearity. I can take that constant out, and I know that if U is a solution, this is going to be 0, and that's going to end up being 0. And similarly, if I give you two vectors, u and v, that solve AX equals 0, is there sum in the null space? Answer is going to be yeah, by linearity again. If I were to consider u plus v and multiply it by the matrix A, I'm going to get AU plus AV. Each of those is a solution, so they give me a 0, and that means u plus v is also a solution. If I give you this matrix, I'm going to plop down some other vector, and I ask, is that vector in the null space of A? In order to be in the null space of A, you need to know if AW equals 0. Well, that's easy to check. You just do a matrix vector multiplication. So you take that matrix and you weight its columns by this, but you're going to find that yes, that is the case. So yes, W is a solution to this problem, so that means it's in the null space. A more involved example here is, let's say that we want to find a spanning set for the null space of A, and then we want to find a basis for the null space of A, and then we want to talk about its dimension. So I'm going to give you a matrix A 3 by 5 matrix. To talk about null A, that means I have to solve AX equals 0. Now note, A is 3 by 5. It has 5 columns, so that means any answer to the question AX equals 0 has to have 5 weights, one for each column. So that means null A is going to be a subspace of R5. But is it going to be one-dimensional, two-dimensional, zero-dimensional? You just solve AX equals 0. You row reduce. The matrix is pretty close to echelon form. All we need to do is to create a 0 above the second column pivot. When you do this row reduction, you're going to get the following system. There are 2 pivots, and that means there are 3 free variables. Any answer to this problem has a vector with 5 components. x1 and x2 are basic variables, they're pivot variables, so you can write them in terms of the free variables. And then the other ones are just as is, x3, x4, and x5. What this allows us to do, as always, is use vector properties and split this up into a vector in terms of x3, a vector in terms of x4, a vector in terms of x5. So I'm going to call this u, I'm going to call this v, I'm going to call this w. Any solution to this problem, it's going to be a linear combination of these 3 vectors. So clearly, this set u, v, w spans null A. These 3 vectors and any linear combination of them create the answers in null A. It'll create all of them. But are they a basis? Are they linearly independent? Take a look at the 3 variables. In order to make this row add up to 0, I would have to select x3 equals 0 to knock out that first pivot. In order to make the sum of these three vectors equal to 0, I'd have to take x4 equal to 0 to knock out that pivot. In order to make these three vectors add up to 0, I would have to take x5 to be equal to 0. So the answer here is yes, this is a basis. x3 equals x4 equals x5 is 0 is the only way to get the 0 solution. So that means they are linearly independent. If you want a basis for the null space, all you have to do is solve the system and get an answer. It's a spanning set, and it's always going to be linearly independent. In this case, the dimension of the null space is 3, and so that means null A is a three-dimensional subspace in R5. The dimension of the null space is always going to be equal to the number of free variables in the solution set. And the number of free variables is always going to be the number of columns subtract the number of pivot columns. And so we are going to make a definition. We will say that the rank of a matrix that is m by n is the number of pivot columns. And then this kind of gives us a nice little theorem. This is called the rank theorem. If I give you a matrix that's m by n, then the number of columns, n, has to be equal to the rank of the matrix, the number of pivot columns, added to the dimension of the null space, which is the number of non-pivot columns. If I tell you something like a matrix is 7 by 6, and if I tell you that the dimension of its null space is 5, that tells you immediately that the rank of the matrix is equal to 1. There's only one pivot column.